Um, let's talk about NFAs some more. Actually, today we're going to talk about NFAs versus DFAs. So comparing the capabilities of each of these two types of machines, the NFAs and the DFAs. All right. What I want to talk about, so how about this? The languages that can be accepted by a DFA. Those are called the regular languages, right? The regular languages, those are the ones which can be the language of some DFA. I would like to talk about the similar category, but for NFAs. What is the all possible languages which can be the language accepted by some NFA? So what about NFA languages? Now remember, the NFA is like a DFA, but it has like more capabilities or more things that you're not allowed to do on a DFA, but you can do on an NFA. And in fact, every DFA already counts as an NFA, right? Like a DFA is still legal if you consider it to be an NFA, whereas the other way around is not true. So I'm going to say any DFA is already an NFA, right? If you start with a DFA, it does obey all the properties that are required for it to be an NFA. So that means that any regular language can be the language of an NFA. Right? If you have a language which is the language of a DFA, automatically it is the language of an NFA because that DFA can also be considered to be an NFA, right? The real question is kind of the other way around. Are there languages which you can do with an NFA but not DFA? And the answer to this question is, in fact, no, there are not. Actually, the languages that you can do on an NFA turn out to be the same as on a DFA. So I'm going to say it this way. Well, let me just ask this question. Are there languages accepted by some NFA but not by DFA? And the answer to this question, this kind of, in my opinion, sort of a surprising answer is no. I'm going to write it with this. Can you read that? I'm just trying to play around with my different pens, whatever. The answer is no, there is not. Another way to say this, I will say this in a more detailed way. Let me write this as a theorem. L is accepted by some NFA if and only if L is accepted by some DFA, right? If you want to write it as a theorem. It's true. If you have a language and it is the language of some NFA, that's equivalent to it being the language of some DFA. This is an if and only if. Remember, if and only if means like it means really two separate things. It means if it's accepted by NFA, then it's accepted by DFA, and it also means if it's accepted by DFA, then it's accepted by NFA. So in this case, there's sort of two directions, and this direction of the if and only if, that is DFA implies NFA. This part of it is obvious, since I said this a few times already, every DFA is an NFA. We can just consider it to be an NFA. All right, it's the other way around, which is not obvious, and like I said, in my opinion, kind of surprising. So this is what we're going to be talking about today, is this other way around. And we're not going to actually write this out as a formal proof, because you'll see there's actually kind of a machines type construction that we can do that that justifies the other way. But I'm just going to say this, for now I'll just say, whoa, this part needs work. All right, but that's what we're here for. That's what we're going to talk the rest of today at least about. All right. What the theorem means is that, if you believe me, it means that any language of an NFA could also be done on a DFA. So I'm going to give you an example of what that means. I see a lot of people just rolling in. Maybe I hope you didn't all try to go to the classroom. Remember, we are doing remote every Tuesday and in person on the other 2 days. Sorry if that's been confusing.
Yeah, I was up there.
All right, you can always tune in from the classroom. I just won't be there. Okay, so any language of an NFA could also be done on a DFA. Here's what I mean by this. For example, here's a sample NFA that we had last time, maybe the time before. I don't know. All right, this is an NFA, and the language is, anybody remember this example? Can you say what the strings look like that are accepted here? And we're going to start here, end up either here or here.
Everything on AB. Everything in AB.
I don't think it's quite everything.
Am I looking at the wrong one?
Maybe. We did several variations of this example.
Is it A to the N, B to the M?
Yeah, the language here is A to the N, B to the M, something like that. Any bunch of A's followed by some amount of B's, but they are not. I'm seeing something funny on my Zoom screen that probably nobody else is seeing. Two of you who are next to each other on the Zoom are like both looking off to the side. It looks like you're looking at each other, but you're not. You're just looking at your roommate or something. I don't know. I thought that was funny. Yeah, the language of this is A to the N's followed by B to the N's. You could do a bunch of A's. You could stop if you want. That would be accepted. And then you could go down here and do some B's, and that would be accepted. But you can't do more A's from here. Okay. Anyway, this is an NFA, and that's the language. Could you make a DFA for the same language? So we could, in this example, we could also do this on a DFA. Although the DFA for this is necessarily kind of complicated. I had to sort of think this through. Here's what I came up with, and it's not so important exactly what this answer is, but this is what I came up with for the DFA for the same language. All right, this is a DFA whose language is the same thing. Any power of A's followed by any power of B's. All right, so this is a DFA with the same language. Now, if you really believe me, the theorem that I said a few moments ago is that actually the capabilities of NFAs and DFAs are the same. If there's a language you can do with an NFA, then automatically there is a language, or then automatically you can make that same language using a DFA. So really what we're going to talk about is actually there is a procedure that you can, like these two diagrams here, they look kind of, to me at least, they look totally different. But in fact, there's a procedure, a specific process that you can go through to start with this diagram and convert it into this one. All right. There is a particular construction that you can do that will convert an NFA to a DFA. So we will learn a construction to convert NFA and turn it into an equivalent to DFA. All right. And in fact, the way that I did it, I mean, I used that process that I'm about to tell you how to do it. I used that process to create this diagram based on the first one here. Now they look pretty different, and the procedure, it will take you a few minutes to do this process. So it should not be immediately clear. How did you go from this first one to this second one? But you know, that's what we're here for. All right. The idea, so this construction has a name. It's called the subset construction. All right, the subset construction. You know, we already learned about something called the product construction. That was a way that you can take two DFAs and combine them into some sort of larger DFA by doing pairs of everything. The states of the resulting thing are pairs from the original two machines. The subset construction is a way in which you start with an NFA and you create a DFA out of it. And the basic idea is that every state of the DFA corresponds to a subset of states from the NFA. So any subset of NFA states creates a DFA state. This is the basic idea. Let's. I think rather than try to explain it all in words, let's just try to do this on an example. I will sort of explain as we go through this example. And I would like to. We might as well just use the example that I wrote before. So I'm going to start with the same NFA from before. It has epsilon transitions, of course. This is my original NFA. And if you want to do this procedure, you have to give names to these states. And I am going to call them Q0, Q1, Q2. All right. So the original states, the NFA set of states, is, you know, it's this, Q0, Q1, Q2, right? The DFA will have a different state for every possible subset. So we're going to list out all possible subsets. In this case, there are 8 of them. This is something that you, I'm sure you did once when you learned about the power set in your early life. I'm going to list all possible subsets. There are some subsets which have only one element in them. There are 3 of those. I believe there are 3 subsets of 2 elements each. Q0, Q1, Q0, Q2, and Q1, Q2, right? Any other subsets? There's actually 2 more, but they're kind of stupid ones. You want to shout them out? Embrace the stupid. I'm looking for different subsets of this original set.
The complete set?
Yeah, all those
Q0,
elements
Q1,
together.
Q2.
Yes, that counts as a subset. Q0, Q1, Q2. And one more.
Does the empty set count?
The empty set. Yes, thank you. Thank you for embracing the stupid. Yeah, you always get the empty set and the full set of everything. They count as subsets. All right. So we have 8 subsets here. Does anyone recall there's actually a cute formula for just to use as a rule of thumb? How many subsets are you going to get if you start with, say, n elements? Can I just put this in parentheses? If we have n, I would say, states to begin with.
2 to the n.
Yeah, we will get 2 to the n subsets. So this is a little rule of thumb to make sure that you got them all. Here we had 3. We ended up with 8, which is 2 to the power 3. All right. Anyway, these 8 things become the states of our DFA. So our DFA has these 8 states. All right. So I'm going to start drawing my DFA. It will have 8 states. Although it turns out in this example that most of them end up being irrelevant, so it's actually not going to be so complicated as it seems. But it will have 8 states, and I'm not sure I can possibly keep them all here. Let me see if I can leave that one over there. I scrolled to the left. Can you believe it? Going crazy here. All right. So I am going to draw those 8 states. I'm going to list them in a convenient way, but I'll put the like biggest one here, and then I'll write the 2 element states here, Q1, Q2. Now I know what the picture is going to look like, so I'm arranging them so that none of the lines will cross over, just as a personal favor to everyone. Let's put Q0, Q1 here, and then Q0, Q2 here. Sorry, I didn't quite leave enough space for myself. I hope you have more room in between them than I do. And then I'm going to list out the single element states. So I have Q0, Q1, Q2, and the empty sets. The empty set gives me a state too. All right, here are my 8 states. Now, I just have to tell you, how are we going to write the arrows? How are we going to decide the starting state? And how are we going to decide the accepting state? All right. Let's say the starting state first of all. So all of these questions are answered by looking at the original diagram and somehow translating features of the original diagram into the diagram that I'm drawing here. So let me say the start state is, now it's reasonable to say, well, the starting state over here is Q0, and so it makes sense to start at Q0 over here in the NFA. That's actually not quite true. Here's the real way to do this. The start state is the set of all states reachable by epsilons from the NFA start. All right, so this you have to be a little careful, but you look at the starting state here, and you want to choose what are all the states I could get to from there, including this state itself, but any other states also which I could get to using only epsilon transitions. And in this particular example, you can get anywhere in this whole diagram using epsilons, right? You could go epsilon up to Q1, you could go epsilon down to Q2, and of course you could get to Q0 just starting at Q0. So in this example, it's going to be Q0, Q1, and Q2, all right? You take the starting state of the original NFA plus any additional states you can get to by doing epsilons. And so in my DFA that I'm building here, this is the starting state. Put that arrow there. All right. That's the starting state. What about the accepting states? I'll tell you how you find the accepting states. The rule is any state over here which includes one of the accepting states from the original diagram, becomes accepting over here. And so in this example, Q1 and Q2 were accepting, and so any state over here which has a Q1 or a Q2 in it becomes accepting. So there's going to be several of them. This starting state would be, because it has a Q1 and also Q2, anything with a Q1 or a Q2 in it. So this one is, this one is, this one is, most of them are, right? This one is, and this one is. The empty set is not, and the Q0 by itself is not, but all the other ones are accepting states. So I'm going to write that down also, what I just did. Accepting, I'll say any state containing an NFA accept state will be accepting in the DFA. All right? This is how you decide where the accepting states are. And finally, how do you draw the arrows? This is the most complicated part. How do you draw the arrows? I'm going to try and say in words, and I'll have to scroll away from the picture for now. Hopefully your piece of paper is bigger than what I'm writing on. Here's how the arrows go. So I'll say the arrow points to, sorry, I'm going to say the set of states reachable from any state in the subset. Using that letter, and I'll put parenthetically or epsilons. What? Sorry. This is a little confusing. We need to try some examples to make sense of what I meant by that. But it says the arrow, you're going to draw in the arrows. The arrow points to the set of states that are reachable from any state in the subset when using that letter or perhaps some epsilons. So let's see if we can do this. Let's start with the starting state and try and draw in the arrows. There's going to be an A arrow and a B arrow. There will not be any epsilon arrows because what I'm trying to create here is a DFA. So that means it's not allowed to have epsilons. So from this state here, let's ask ourselves, with the A arrow, the question is, if I start in any three of these states and I do an A, what's the set of all possible states you could end up with in? So looking over here, starting in any of those three states and you do an A, what is the set of all possible states you could end up in? Maybe it's still all three of them, but maybe it's not. Can anybody say? You start in any of these three states, you do A. Where could you finish up? Sorry, I meant to say, you can do A, you could also do epsilons. Does that change your answer? She said Q1. I agree that Q1 is the only one, like, you cannot arrive in Q0 by doing an A from any one of these states, right? You can arrive in Q1. Is it possible to arrive in Q2? I said you can do an A or possibly epsilons. I left that out. I didn't make a big deal of it. Yes, you can arrive in Q2 by doing an A followed by an epsilon. All right, so in this example, the arrow with the A goes like that. And let me just, just because I know this is a little confusing, but just to explain this particular arrow here, what that means is from any of these original states, Q0, Q1, Q2, if we do A, or possibly some epsilons, any number of epsilons, we can end in Q1 or Q2, but we cannot end in Q0. And that's why the arrow goes to Q1, comma Q2. All right. How about the B arrow from the starting state? Where should the B arrow go? Again, you got to look over here and ask yourself, considering all of these possible states together, where can we end up after having done a B and perhaps some epsilons? Q1, Q2? Any other idea?
Would it just be Q2?
Yeah, it's just Q2 in this case. If you do a B, certainly you can end up in Q2. And actually, even if you're doing also epsilons, there's no way to end up in Q1 or Q0 after having done a B, right? So it's only Q2 in this case. And so the B arrow from here goes all the way over there. All right. I said I was going to do this without crossing the arrows over. I don't know if you're nervous about the way that one went. It's going to be fine. Don't worry. Trust me. All right. Now we got to just continue filling in the arrows. Now your strategy, it turns out in this case, many of these states are going to be irrelevant. So my strategy is going to be, I'm just going to start from the starting state, fill in the arrows, and then go to the states which result and fill those arrows in. It turns out actually, for instance, there's no way to reach this state, Q1, in this particular example, is unreachable from the starting state. So it's going to end up being irrelevant, this state here. You don't actually have to think about all of them. Start at the starting state and then follow the arrows. Let's do this one next. Q1 and Q2. All right, we have to insert an A arrow and also insert a B arrow. What do you think? Anyone want to shout it out? What do you get from A? So from Q1 and Q2, that means you look over here. If I'm in one or the other of these and I do A, perhaps with epsilons too, where could I end up?
Did you say start in any of
Q1
those
or
states?
Q2?
Yeah, you're gonna imagine that you start in either one of these,
Okay.
and you do A and also some epsilons if you want. Yeah, where could you finish? I think somebody said you could end in either Q1 or Q2, right? You could end in Q1 by just doing A and stopping. You could end in Q2 if you did A and then epsilon. So Q1, Q2, when you do A, it goes back to itself like that. Q1 and Q2. How about from Q1, Q2, when you do B, what does that look like? If you're in either one of these states and you do B, where could you end up?
Q2.
Yeah, just Q2 in this case. So the B arrow from here goes like that. Right? Okay.
Are you always starting from the one that you just did for the next arrow?
Yeah, I mean, you can fill in the arrows in any order you like, but it makes sense to start with the starting state and then just kind of continue from wherever those arrows are pointing. Yeah. Okay, let's do this one now. Q2. So far, everything is like going down to this one with the Q2. So over here, what about the A? You look on this picture and you ask yourself, if I begin in state Q2, what's all the states I could end up with if I do an A and possibly epsilon? So I start in Q2. Where can I end up if I'm doing A and maybe epsilons?
Can I ask a question about the last part?
Yeah, sure.
Yes. Why would B not go back to Q1, Q2? Because like, can't you do either B or an epsilon?
You can, but there's no epsilons going back up to, like the arrows aren't going the right way here.
Okay.
So from Q1, if you want to do B, the only way to do it is this epsilon then followed by a B. If from Q2 to do B is here, but you can't get back here by epsilons. Is that what you meant? Yeah. Yeah, it's a little easy to mess these up, I find. And if you draw one arrow, it might cause you to screw up the whole rest of the picture, unfortunately. What do you think? Anybody have a feeling? The A arrow from Q2. If you start in Q2, what's the set of all states you can reach by doing A?
Just Q2.
I think actually, if I start in Q2 and do A, I can't even finish in Q2, right? I see some people just sort of shaking their heads. What does that mean? Yeah, the empty set. From Q2, you can reach nowhere by doing A, right? That means this goes to the empty set. That empty set state is important to have in the DFA when you draw this. Okay, what about Q2 and a B? What do you say? If I start in Q2 and I do B, I think it goes back to Q2 and that's it, right? You can't get to either of the other two states. So I'm going to put one of these. All right? Okay. Keep on drawing arrows. I have filled in all the arrows here and here and here. So actually, we need arrows from the empty set. This actually, you will you can just kind of remember this. Empty set always has easy arrows. What is the outgoing A from the empty set? The way you have to think about it is over here in this diagram, starting from nowhere, where can I get if I do an A? The answer is nowhere, right? That's how you have to think this through. If you're not starting at any state, what are the states you can finish with? If you do A, the answer is you cannot go anywhere. And B similarly. So this actually is always going to happen. From the empty set state, all arrows will loop back to the empty set state. This will be the case in every example. And in fact, actually, because of the way the accepting states are chosen, the empty state is always a rejecting state, is never accepting. So in this construction, the empty set always becomes a permanent fail state in this, if you're doing it right in this DFA. All right. But anyway, we're done at this point. All of these states have outgoing arrows that have been filled in. That means these other states on the diagram are unreachable from the starting state. So I'm just going to kind of, we don't need these, all right? These blue ones here are what the book refers to as unreachable from the starting state, which means they don't actually have any effect on the way that this DFA works, and you might as well leave them out. You could, if you want to, try and fill in all the arrows, but that's a lot of work and it doesn't affect your answer at all. And so my full answer is just those 4 states that I ended up using. So if I wanted to, I could redraw this. So my answer is, I'm just going to leave out the names here. I'm redrawing the same DFA. Like that. I think I drew everything, right? And wouldn't you believe it? That is the same DFA that I wrote at the very beginning. Remember I said this one is equivalent to that one? That second one, that is the one that we just got by doing that whole big process, all right? If you ignored the names. I didn't tell you the names, but of course the names are not actually really part of the DFA. They're just names for everything. Okay? So this is you know, I just said there was some kind of mysterious procedure by which you can get from this picture to this one. We just did it. It's called the subset construction. All right? I want to do one more example. Does anyone have any questions at this point? It looks kind of like ramblings of a crazy person. I feel like I should put this on a bulletin board on the wall with pieces of string tied onto it or something. But yeah, this is how it's done. Any questions?
Do you mind just going through how you got the unreachable state again?
Yeah, sure. So it's because we began at the starting state, and I filled in 2 arrows from there. One goes here, one went here, right? And then from this state, I filled in 2 arrows. One was a loop back, and the other went down here. From this state, I filled in 2 arrows, and then from this state, I filled in 2 arrows. Now, all of these states have had all of their arrows filled in, which means there is no possible way to get to those other 4 states. And so we can just leave them out.
So just from when you're in the empty set, you don't have to consider the A's or the epsilons. You just the A or the B, no epsilons are considered then.
We always consider epsilons also. Oh, you mean? Do you mean like shouldn't there be an epsilon like that?
No, like if you started from the empty set, if you don't have anything and you're in the NFA and
Yeah.
you had an epsilon, does that bring you to 1 then, or do you have to? Am I missing something?
No, if you're in the empty set means like you're not in any of these states. And then you do epsilon, you're still not in any of those states. That's the idea.
All right, I see it now. Okay.
Yeah,
Thank you.
it's kind of stupid. I mean, the logic kind of breaks down a little bit, but yeah, the empty set means you're not anywhere, and so whatever you do, you're still not going to be anywhere. Right?
Thank you.
All right, let's try another example. This is a little tricky, and I have one for you guys to try too, but maybe we'll just start off next time because I don't think we're going to have enough time to do another. Okay, I have another DFA in 3 states. I'm sure you can imagine this can be very difficult if there's a lot of states in the original DFA. It makes the NFA is what you start with. If there's a lot of states, it makes it very complicated to do the subset construction. That's what we're doing here. All right, let's say that's the whole. This is the whole NFA. First of all, we should make names for things. You can name these things whatever you want. I'll just do similarly Q0, Q1, Q2. And we're going to draw each of our subsets. Now, again, we have 3 states to begin with, so we should expect 8 total subsets. Would you mind? I'm going to sort of start this off a little differently, which ends up being a little easier. Let's just start drawing with the start state, and then make new ones as we go. What I mean is, instead of like trying to make my diagram with all 8 of them to begin with, I'm just going to start with 1, and then every time I make a new arrow to somewhere else, I'll just invent a new state as we go. And then whichever ones are unreachable, they will just never appear on my diagram. So anyone want to tell me what is the starting subset? That would be all states from the original diagram which are either the starting state or anything which is reachable by epsilon from the starting state. What do you say?
Q initial.
Yeah, I think it's just this, Q naught. This example is a little easier because there are no epsilon transitions in this one, so it's a little less confusing from one step to the next. You don't have to think about epsilons. Our starting state in the NFA, in the DFA, this is the NFA. I am creating the DFA. Our starting state will be this set Q0. Okay. We're going to draw the arrows now, right? So the A arrow from this state, Q0, you look at the original picture and ask yourself, where's all the states I could reach by doing an A? And possibly epsilons, but that doesn't matter this time. What do you say?
Would it be the big Q0, Q1, and Q2?
Not quite. So you should say starting in Q0, because I'm in Q0 from here. Starting in Q0, where can I get by doing A? Just one A.
Q0 and Q1.
Yeah, that would be, you could get to Q0 by doing A, or you could get to Q1 by doing A. That's it. If you wanted to get to Q2, you got to do A twice, which we're talking about one letter at a time. So Q0 and Q1. So I'm going to make a state for that. And an A, like that. All right. From Q0, if you do A, you can get to Q0 or Q1. Okay, what about from Q0, if I do B, where could I get to? I think somebody said Q0, right? It sounded like a whisper in the wind. Q0. Yes. If you're at Q0, sorry, I don't want to scroll there. If you're at Q0 and you do B, you can only end up at Q0 again. All right, excellent. Now, I have filled in all outgoing arrows from here, so now we'll move on to here. let's do the A and the B from here. What about the A from Q0? So your thought should be, if I'm Q0 or Q1 and I do an A, what are the states which I could end up in? Yeah, it could be any of the three states, 0, 1, or 2. So I guess I'll just put that over here. Q0, Q1, Q2. From Q0 or Q1, if I do A, I could go to any of those three. And what if I do B? From Q0 or Q1, if I do B, where could it go? Yeah, from 0 or 1, if I do B, I could end up in 0 or 2. So that's another new state that I need to draw. Q0, Q2. Right. All right, we're still going here. We just got to continue drawing outgoing arrows. Hopefully this will end, you know, it'd be nice if we didn't have to just keep making the diagram bigger in every step, but we're gonna do what it takes. Let it do what it do. Let's look at this one. From 0, 1, 2, if we do A, where does it go? If we do B, where does it go? What do you think about A? Starting from any state, where can you get to if you did an A? I think we can again get to any state if we do A from any of these three. So this will be an arrow like that, back to itself. What about if I do a B from any of these three states? If I do B, I think that goes to Q0 or Q2, but not Q1, right? You can't get to Q1 by doing B. So that's like this. All right, am I done yet? What's that?
No, you have to do that. Q0, Q2.
Yeah, I got to do, remember we need 2 outgoing arrows from every state. So now we have to look at this one and draw the arrows in. Hopefully we won't have to make any new states, but you never know. So Q0, Q2, if I do A, it looks to me like that could land me anywhere if I did A, right? From 0 or 2, if you do A, you could get to anywhere. So that one goes back here with an A. And from Q0, Q2, if I did B, what do you think?
Go back to itself.
From Q0 or Q2, if I do B, I think actually that does not go back to itself. Anybody?
Go back to Q0.
Yeah, just Q0, right? If you're in 0 or 2 and you do a B, you can't end up at Q2 again. So it's just Q0, and that is my first state. All right. I'm glad I didn't have to create a new state for that, because now we're really done, right? We have written down all the outgoing arrows from everything.
For the A, for the Q0, Q2, how does it get back to Q2?
Oh, I think perhaps, yeah, that is not right. This A down here, it shouldn't be there. Thank you for that. Did I mention this is easy to screw it up? It is. I hope it doesn't make a new state. Where should it go instead of that? Q0 and Q1. Yeah, let me think. So in Q0 or Q2, if I do A, yeah, I agree. It should be 0 or 1. Like that. Anybody else agree with that? I hope that you noticed that. Thank you for catching my mistake. Okay. We are done drawing the arrows. Actually, there is one more thing we should do before we're not totally done with this DFA. What else do I need to do?
Accepting states.
Yeah, we have to indicate which are the accepting states, and this is easy to do. Remember, the rule was any you look at what the accepting states are originally, and then anything down here which contains an accepting state as an element becomes an accepting. So in this case, Q2 is accepting, so any one of these which has a Q2 in it becomes an accepting state. So in this case, it would be this one, because it has a Q2 in it, or this one, because it has a Q2 in it. Those are my two accepting states. All right, and that is my DFA. And the whole point of this whole construction, remember, the reason that we would want to do this at all is because the language, at least this is the idea. I don't know how obvious this is, but the language of this DFA is the same as the language of this NFA. That's the idea. We got a few more minutes, but I think I'm going to leave it at that. So next time, like I said, I want you guys to try an example, and we'll also try and describe or try and give you some reason to believe why is it that these two things have the same language. This is a complicated construction that we did here, but we are going to get something with the same accepted language. All right, I think I'll leave it at that. I will see you in person tomorrow, or on here if you don't want to come in person.
Thanks, Professor.
Thank you.
All right.